In this segment, we will solve a problem from axial loading cases, and the problem goes like this. There is an aluminum rod and there is a steel rod. The length, the area, the Young's modulus and the thermal expansion coefficients for both aluminum and steel are given here as data, known data. And it's known that when they were assembled in this fashion, there was a gap of 0.5 mm between them, and during the assembly the temperature was T0, which was 20 degrees centigrades. And then what happened, for some reason the temperature was increased to 140 degrees centigrade, and we are supposed to find out what is the stress that gets developed in the aluminum rod and what is the change in length or elongation that has happened in the aluminum rod. So these are the two things we are supposed to figure out. Now, how to think about this problem is, see, if they were not placed side by side like the way it has been done here, they would have expanded because of this change in temperature, and because they are placed in this way, so they will not be allowed to expand, and once they touch each other they will not be able to expand anymore. So that means there is an expansion because of temperature difference, but then there is a change in length or compression because of the force that gets that each is applied by each other as a reaction force. So these two will make the total elongation to be in a way 0.5 mm. Okay. Now, so to solve that problem, what we can see is the total change in temperature, say delta T, is 140 minus 20 is 120 degrees centigrade. Now, if we denote delta T to be the total expansion that would have occurred if they were not restricted, is given by, say, alpha aluminum, sorry, L aluminum, length of aluminum times alpha aluminum times delta T. So this is the length which the aluminum rod would have expanded, plus length steel times alpha steel times delta T. Delta T is common for both. If you substitute the values here, you will get an elongation of 1.347 into 10 raised to minus 3 meters. That means 1.3 mm almost. But now because they are getting compressed because of their internal forces, so if we draw the free body diagram, so they will look something like this. So a force P is acting on the say aluminum rod, and the exact same force P will be acting on the steel rod because there are no other external loading which is getting applied. Now, because of this force P, they will be shortened. So now let that be called delta P. But then this is an elongation, this will be an compression, and if this is considered negative, so then what we will have is delta T plus delta P will be, so please note that this is negative and this is positive, will come out to be, say, 0.5 mm. So this is the equation which we should use to solve for P first, and then from once we know P, we know the stress and everything. Okay. Then how to get, say, delta P now? Delta P is nothing but P times LA over EA. plus P times L steel over E steel A steel. Okay, if you substitute all these values and equate it, we can say that all these things are with a negative value because these are compression, and okay, and then what will happen is if you substitute this back into this equation here, and this we know here, we can just solve for P. Okay, now from that we will get P to be equal to 232.39 into 10 raised to 3 Newton. Okay, so so that means so we now know the force of interaction between them. We now just can apply to find out sigma aluminum, suppose, okay, is equal to this force P over area aluminum, and it will be a compressive stress, so we can put a negative sign here, so that will be equal to minus of 116.2 megapascal. And to figure out delta aluminum, what we can do is the length A times alpha A times delta T, this would have been the free expansion, but because of this force, a contraction happened of this value, so P L aluminum over E aluminum and A aluminum. So if you substitute the values, you will get it to be 0.363 millimeter. So this is how you can, if you think from basics, it's not very difficult to solve the problems. See you in the next segment.